So I prepare, this is a condensation of things that I was planning to do in 2 lectures. So I don't know what we are gonna be able to cover today. And for me, the most important thing is really to get your questions. So I'm very happy to to skip things for the sake of having more discussion and try to answer more of your question. Also, this is the end of almost the end of this week of Summer Institute. So you heard a lot of presentations by the other speakers, and I really hope that this, I'm sure actually that these other presentations inspired you questions. So what I hope from this conversation is really to try to learn from you what are the things that you think are more interesting, the things you want to know. And of course, I wanted to start by giving you my point of view, but then I'm happy to take my point of view shorter and hear your questions and try to have a bit of a dialogue for what is possible online. Okay, so
yeah, take it away. Thank you.
Yeah, I may start from here. So. So, of course, my presentation is about quantum gravity, and one of the questions, before starting any conversation about quantum gravity, is good to have in mind what is the goal of the pursuit for quantum gravity. And let me say that for me, it's about finding a concrete realization of a quantum theory of the gravitational field. And notice that I'm saying a concrete realization. I'm not looking for, at this point, for the uniqueness of the theory. As Feynman said, it's better to be able to look at the same physical problem having a multiplicity of theories. But the problem right now is just to find one that works. So the goal is asking the question, do we have at least one realization? A realization that is well-defined in the sense that we want to be able to do computations, and being able to do computations in a quantum theory means having a theory that is devoted from infinities. So we don't want ultraviolet, and we don't want infrared divergences in our transition amplitudes of our quantum theory. Of course, the theory should be a quantum theory of gravity, and the best classical theory of gravity that we know, it's general relativity. So general relativity should be the limit of our theory, should be the classical limit of our theory. So far as we know, the world in which we live, and in every case, the setting in which general relativity is constructed, is a world that is 4-dimensional, and it's Lorentzian. So this will be the context, but also it's the starting point of the kind of quantum theory of gravity that I wanted to discuss. And what's the relation with the other fields, in the matter fields? Well, I just want, as in general relativity, I want a standard coupling with the other matter fields. So in this sense, we are not addressing here the question of unification between matter fields and the gravitational fields. What we want is just to discuss the problem of the quantization of gravity in a way that is compatible with the standard quantum matter as we know it. So that's what we want. And I would argue that these things are indeed achieved in the approach to quantum gravity that is loop quantum gravity. And this will be the focus of my presentation. The way in which loop quantum gravity is being constructed is in the philosophy of parsimony, I would say. So there could be different strategies to address the relation between the quantum theory and what we have learned with general relativity. And notice that here I put in as the main thing general covariance. As a more general principle, even more than the strict treatment of the gravitational field in general relativity. So I said parsimony in the sense that we don't want to postulate new physical entities. We don't want to add to the ontology of our theory anything more. In fact, what we want to do is the opposite, is to look at what is dispensable in the quantum theory and in general relativity. And by this process of cleaning, in fact, the process of cleaning that is characteristic of the philosophical work, try to see what is at the core of the theory and what is instead dispensable. So what are the structures in the theory that really encode the physics, that really encode the physical reality of the system that we are considering, and what instead it's, if you want, a mathematical accident that we can remove, and the theory is still viable, is still consistent, even without those structures. So I would argue that in the quantum theory, the background space-time is dispensable. And in the theory of general relativity, the use of the continuous manifold is not necessary. It's just an accident of a particular formulation of general relativity. But in fact, you may have other formulations, an algebraic formulation of general relativity that doesn't make any reference to the manifold. So there is a sense in which those things are there, but they don't belong to the theory itself. They don't belong of the conceptual core of the theory. On the other hand, there are other aspects that are present both in the quantum theory and in general relativity that somehow stays there. And I emphasize in particular the role of the symplectic geometry that is at the base of the quantization as we know it. The procedure of the Dirac quantization is very much based on the structure of the phase space with conjugate variables. And in the same way, we can look at covariant theories in a generalized phase space, where instead of having in Hamiltonian, we promote our variables. We promote time in particular to a variable itself. So what we have is that instead of in Hamiltonian, we took the dynamics is coded in constraints. So because of that, we have a generalized phase space rather than just a phase space. And so constraints are the core of the story. And constraints are always related also to gauge theories, because in presence of constraints, we have partial observables. So observables that corresponds to physical quantities that we can measure, but we cannot predict. So it's only by coupling more than one partial observable so that we can construct gauge invariant quantities. And the presence of these partial observables is something that is there both in general relativity. For instance, typically the clock in general relativity, the time is a partial observable, but this is also something that it's at the core of the way in which we write the quantum theory, in particular in presence of gauges. So you see that there is a transversal link that connects the quantum theory and the general relativity. So let me start, let me notice something. One of the important point of view here is to select what is really at the core of the quantum theory and of general relativity, of the general covariant theory. And on one hand, for general relativity, well, let me start on one hand for the quantum theory. Something that I wanted to highlight has been really the core of the story is discreteness. To me, the discovery of quantum mechanics, and more in general, the discovery of the quantum theory, is the idea, the fact that there is a fundamental quantum discreteness in the physical world. So this comes with the discovery of H bar. And of course, one possible counter-argument is the fact that, well, we don't have only discrete spectra, we also see continuous spectra. Well, if you think for a moment, well, one example of a continuous spectrum is exactly with position and momentum. But once you realize that the position should be, in fact, described in terms of the quantum gravitational field, well, at this point, you may argue that even those spectra should turn out in a full quantum theory to be discrete. So I think really discreteness is the core of the story. There is more on this in the sense that if you look at many reconstruction theorems, so many attempt to derive the full set of principles of quantum mechanics from fewer principles. By postulating discreteness, you automatically get the superposition, you automatically get the Born rule, only starting from discreteness. So in a sense, discrete and superposition are two faces of the same phenomenon, two faces of the same aspect of reality. So that's why I just put discreteness there, because there are the other aspects of the quantum theory somehow can be derived from there. And on the other hand, we have general relativity, from which we have learned about general covariance. So the two messages here are the following. But the first thing is that with the general relativity, we discovered that we need to describe physics in a background-independent way, in which, as I said, the dynamics of the theory is given in terms of constraints. So this is something that is always available with any theory. It's just that with general relativity, this is an obligation. Working with parameterized theory, it's compulsory. We cannot, I mean, in order to go out of this, we have to make tricks and so on. But from this, what we can learn is that this is a formalism that is always available to us. It's just that when we have the gravitational field as a fixed background, it's very easy to treat the other theory in a deparameterized way. But otherwise, the most general formalism is this one of general covariance and constraints. And from the physical point of view, the core of the story of general relativity, as Einstein himself put it in some of his memoirs, is the idea that space-time itself is the gravitational field. So there is this identification. And looking at general relativity in this perspective, it makes completely sense. In fact, also historically, this is how things were understood. It makes completely sense to look at the theory of general relativity as a theory in which we promote the reference frames to fields. So we have this concept of reference fields that is embodied in some mathematical objects that are the tetrads that we will discuss in a second. So, but from this slide, my lesson is that the strategy for the path toward quantum gravity is a path of minimalism. We try to not to introduce new objects, but rather to clean and to preserve only the objects that are essential for our description of quantum spacetime. So in doing so, I argue that even though sometimes this approach is described as being conservative, because we are not changing anything, we are just taking general relativity and quantum mechanics practically as they are. But on the other hand, I argue that this is extremely revolutionary, because this procedure of taking away things from what we mean by space and what we mean by time and what we mean by matter itself. So this procedure, it brings us to a quite revolutionary picture, a quite radical new picture. And so what we have, the picture we have at this point is that we have matter fields, and these matter fields itself, they don't live anymore in a fixed absolute space and time, but they rather live on another field, that is the gravitational field. And I want to, so the kind of unification that is achieved with this procedure is a conceptual unification. Again, it's not a unification in terms of finding a unique symmetry group that allows to describe everything that exists all at once, but there is a conceptual unification in terms, so thanks to which we can describe all the fields with a common language, that is the common language of covariant gauge fields. Covariant quantum gauge fields. So again, we have the fields of the standard model that are described by these symmetries, and we have one more field, the gravitational field, whose fundamental symmetry group is basically the Lorentz group. And this is the starting point for the quantization. This is just one more slide regarding the fact that, as I was saying before, the language of constraints is not just characteristic of general relativity. It's something that can be extended to all the description of all the other fields, in particular for Yang-Mills, also for Yang-Mills fields, which can talk in terms of constraints, and we will have a corresponding constraints that determines how the variables change with respect to a change in the internal boundary frame. And in the same, so we can interpret all the different constraints as the generator of changes with respect to different aspects of our description. In the case of the constraints of the diffeomorphism, it's a change in the location of the spatial boundary reference frame. The Hamiltonian constraints is the change with respect to the temporal location of the boundary. So something that I want to stress here is that a specific point of view that is adopted in quantum gravity, in this approach to quantum gravity, is the idea of describing physics locally rather than asymptotically. So in this case, what I'm doing is to consider a finite region of space-time, and considering a finite region of space-time that is 4-dimensional Lorentzian, determines the presence of a boundary. I am introducing a partition in my space-time, and in this partition, the boundary corresponds to 3-dimensional geometries. So possibly I can choose this, so the normal to this boundary determines a privileged time direction. So I can choose my boundary to be a space-like slice. And this is going to be important for what comes next. Okay, let me skip this for a moment. Maybe, okay, so the resulting picture is a picture in which I wanted to compute transition amplitudes, and these transition amplitudes will correspond to transition from one state of the 3-dimensional geometry into another one. So I can make a partition of my 3-dimensional boundary into parts. I can decide that one part is my in state and the other one is my out state. And everything that is in the bulk, it's what gives me the transition from one state to the other. That is my transition, so it's my transition amplitude, but at the same time, this transition amplitude, it's exactly my space-time itself, is my 4-dimensional Lorentzian space-time. Okay, so this was just the setting, and I wanted to go back. So I wanted to start discussing the most important, I wanted to start from discreteness as one of the most important part of the story in discussing quantum gravity. So quantum discreteness. And I wanted to make a connection with respect to what we know for standard quantum theories such as QED. So in general, when we wanted to give a definition of a quantum theory, well, what we have is a space that is, in the case of QED, is, for instance, the Fock space that, so let me do this. So here, this F is my Fock space, in which the states of the theory are, that is composed, let's say, by the states of the theory. And then I needed to give a algebra of observables. So careful here. This is the most important, in a sense, this is the most important part of the story for the physics, because deciding what are the observables of my theory corresponds to give the semantic of the theory, corresponds to tell what are the physical degrees of freedom that I want to describe. And finally, I needed to give the dynamics of the theory. So of course I can give it given a Hamiltonian or a Hamiltonian constraint, or I can define the dynamics in terms of a transition amplitudes. This is the strategy that I will discuss further in this talk. So, and of course, given a transition amplitudes corresponds to give some Feynman rules to compute those transition amplitudes. So the starting point is that I have my classical electromagnetic field. And then, of course, when I go to the quantum theory, in the quantum theory, in my Fock space is made by excitation of the electromagnetic fields, so I have photons. Okay, so this is how I go from the classical to the quantum theory, and vice versa. Just okay, just I cannot change the slide for some reason. Okay, and vice versa. If now from this theory I want to go back to the classical one, to the continuous one, well, I remove the discreteness given by this quanta. I remove the fuzziness, and I pass from a theory that is probabilistic to a theory that is given in terms of classical equation. So in quantum gravity, things are not different. They are in fact exactly the same. The only difference is that now it's the gravitational field itself, the background that I had before, that is getting made of quanta. There is this fundamental granularity of spacetime, and careful that this is a genuine discreteness, a genuine quantum discreteness. I will tell you more in a second. This is a discreteness that comes directly from the structure of, from the nature of my observables, and comes from the nature also of the dynamics. So both observable and the transition amplitudes are giving me information about this quantum discreteness. You will see this in a moment. So in a quantum theory of gravity, I am on the right side of this slide. I have my fundamental description of the gravitational field in terms of quanta of the gravitational field. So there will be a Hilbert space with some states that are these ones. I will have observables that will be geometric observables because of the identification between the gravitational field and the geometry. And I will have a dynamics defined in terms of transition amplitudes. So what about how I connect back to the classical theory? Well, the classical theory will correspond to take the limit for h bar that goes to 0. In fact, it's more than this. I want to remove the discreteness that comes from a combination of h bar and g. So once I take this quantity to 0, I remove the quantum discreteness of my quantum gravity theory. From a theory that has fuzziness, I remove the fuzziness. From a theory that is probabilistic, described in terms of transition amplitudes, so probabilities, I go back to the classical field equation. The classical field equation that are described by classical quantities, and these classical quantities could be, well, it's the variable that embody the gravitational field, that could be the metric, or better, we will see that are those reference fields, or tetrads, or Vierbein, as you wanted to call them, that are actually, in a sense, more fundamental than the metric. So so what we mean by emergence of space-time here? Well, it's not a proper emergence in the sense that when we talk about strong emergence, we want a new theory that cannot be reduced to the more fundamental one. In this case, it's just the usual relation between quantum and classical. So and most importantly, there is a sense in which we have properties of the classical space-time that are still present there in the quantum theory. So for instance, the symmetries, the Lorentz symmetry, it's still there in the quantum regime. The relations between quanta, so the adjacency relations and the distances that are coded by the gravitational field are still there, and so on. So the main difference here is that the object that we are treating, it's fully a quantum object in the quantum regime, and because of that, we should really think of space-time itself as a quantum process. This is what I was starting to discuss before. So space-time itself, it's a process. It's being the gravitational field is dynamical, and so space-time itself should be thought in terms of processes. And of course, something inherited from general relativity is the fact that there is no absolute space. There is no sense in which there is still a Newtonian time, but this is something that is already true at the classical level in GR. Again, the difference between the classical level and the quantum level is just the impossibility to find strategies to reintroduce an artificial time. So this is something that is available in general relativity and becomes impossible, let's say, in quantum gravity. So that's why the passage from having the constraints that are the Hamiltonian constraint in classical GR, in the moment in which this Hamiltonian constraint is promoted to the Wheeler-DeWitt equation, so it's promoted to have an operator that gives the Wheeler-DeWitt equation. Well, in this case, the reintroduction of of something that allows for the parametrization of the theory is much more difficult, and that's why we talk about the problem of time there. But again, I wanted to stress the fact that is just something that is in fact inherited from the classical theory. So let me go back to discreteness. I wanted to stress the idea that in the same way in which I can think of quantum mechanics as the discovery that there is a minimal amount of energy, there is this quantity that is h bar that appears. The way to understand the h bar, it's in terms of minimal cells in the phase space. So in quantum mechanics, I was stressing before, we start from a description in which we have a phase space. And quantum mechanics is the discovery that we have to treat this space, this phase space, as having some minimal cells with the sites h bar. Similarly, we can think of quantum gravity as the discovery that there is a minimal sites also for geometrical quantities, and in particular, well, the first geometrical quantity that was discovered was the Planck length. It's very easy to understand where the Planck length comes from. So this was a realization by Bronstein that because of the uncertainty principle, of course, if you wanted to localize things in a space that is smaller and smaller, you need an energy that is higher and higher. But at a certain point, if you localize a lot of energy in a small space, this energy is forming its own black hole horizon. And hence, the black hole horizon that forms is exactly of the size of a radius L Planck, that is the minimal size beyond which localization becomes impossible. So this is an heuristic way in which the presence of this minimal length scale is derived, but in loop quantum gravity, this comes in a somehow first of all, it comes as a prediction of the theory, and it comes from the fact that we are really treating general relativity as a gauge theory based on the Lorentz group. But remember what I told you before, that one important aspect is that we are considering finite region of space-time. So let me tell you what happens at this point. Well, the first step, as I was mentioning before, is that you don't have to think of general relativity using the metric formulation. The tetrad formulation, that is equivalent, actually is not equivalent, is more rich than the metric formulation. It can be seen as more fundamental because it's required for the coupling of matter. So if you wanted to couple spinors in GR, you cannot do it with the metric, you need to use the tetrads. More than this, once you want to study general relativity as a Hamiltonian theory, but the first step in doing so is to use the so-called ADM formalism, in which again you have to select a foliation of your space-time. But we said before that when I work with finite regions with a boundary, so the boundary itself selects a preferred foliation, so I can use that. And in particular, you see, the tetrads tetrads are basically quadruplets of vectors that sum up to 0. So they are all based on of the same point here. But once I consider a foliation, so I have a normal to my foliation, and on the foliation I am left with a triplet. So just the triads. So let me consider these triads now. So when I go to the Hamiltonian formulation of general relativity, I discover that these these densitized triads are canonically conjugate to a connection that is called the Ashtekar connection. So the tetrads are those three-dimensional reference frames, and they are conjugated to the variable that knows about the curvature. And so notice the fact that the triads now on this foliation, they have a rotation invariance. So I am free to choose the orientation of my triads. So they are invariant under rotation. That means that there is an SO3 symmetry, or better for the quantization, we want to look at SU2. And now all of you should know that SU2, we know everything about the quantization of variables that are in SU2, because this is exactly what we do when we quantize the angular momentum. So we discover, so this L corresponds to my gravitational field operator, my triads. So I promote my triads to operators. That's the first step. Once I do that, so the triads corresponds to generators of the SU2 transformation, the generator of rotations. And I discovered that this operator acts as a left invariant vector field. So there is, at this point, well, I need one more thing to appear. It's not appearing yet. Yeah, oops, okay, obviously I left the good moment. So let me tell you what happens with respect to my triads. I have this set of vectors L, and this set of vectors we say that they sum up to zero in the sense that they are vectors that are all based on the same point. But there is a beautiful mathematical theorem, geometrical theorem that goes back to Minkowski that tells that once you have a set of vectors that sum up to zero, there is a unique polyhedron that is associated to them. So you can think of all these vectors based on the same point, and I can associate a surface whose size depends on the length, on the modulus of this vector, and so this allows me to compose a concave polyhedron. So especially in the case of tetrads, so this will correspond to a tetrahedron. But this is more generic, and in fact, I can have more vectors and have more complex polyhedra in this way. And so from the Minkowski theorem, I can do the quantum version of the Minkowski theorem, that is the so-called Penrose spin geometry theorem. So I have a quantum version of this polyhedra, and the beautiful thing is that what the spin geometry theorem tells me is that even if I start just with these abstract generators of SU2, well, because of this theorem, there is a notion of geometry that is already present there. So without discussing, without introducing manifolds, without introducing any other structure, from this algebraic formulation, at the quantum level, I have already a notion of geometry. And I told you, so associated to the tetrads, I have my connection. In fact, for the sake of the quantization, what I want is the holonomy of the connection. So I exponentiate the connection to create a well-defined operator. And this connection becomes relevant when I consider more than one polyhedra, more than one, not just the tetrads in a single site, but multiplets of generators of SU2, multiplets of these tetrads in different sites. And what the holonomy of the connection does for me is exactly the same thing that in quantum field theory, in particular in quantum field theory on a lattice, the Wilson lines or the Wilson loops does for me. So I compare the gravitational field in different sites, but comparing the gravitational field in different sites is equivalent to ask how much curvature there is between these sites. And this is what the holonomy of the Ashtekar-Barbero connection does for us. So this is the setting, and I say, of course, from these generators of SU2, from the tetrads, I can construct the most basic geometric operator, that is the area. But just by using these operators, I can construct also other geometrical quantities. I can construct a volume operator, I can construct an angle operator, and I mean, whatever geometrical quantity you can think about. So starting from these objects, you can construct a corresponding observable. The result, the main result of loop quantum gravity, in fact, it's the celebrated result by Rovelli and Smolin of 1995, is the fact that this area operator has discrete spectrum. Well, and then you can look that also the other geometric operators have also discrete spectrum. So I have discrete eigenvalues. I have, of course, that these operators do not commute. So there is this genuine non-commutativity typical of the quantum theory. And of course, there is a superposition in the sense that I can write states for this theory, and these states, the most generic states in my Hilbert space, will be actually a superposition of states. So we have a superposition of geometries, and in general, I can construct coherent states. That means that I can construct a superposition such that it's picked on a particular classical geometry. And I want to stress the fact that the states I'm talking about, they are states of space, not states on space. Let me say something. So I stressed a lot the fact that this quantization is based on the Lorentz symmetry. So what is happening is that the Lorentz group, when I consider, the quantization is based on the full Lorentz symmetry, the full Lorentz group. Practically, when I want to write states at a given time, the Lorentz group breaks in boost and rotation. So on my three-dimensional space-like surface, I'm left just with the rotation group. And we have seen that this is the origin of the genuine discreteness of the theory. This discreteness in the eigenvalues of the geometric operators. On the other hand, there is also another symmetry that is characteristic of general relativity, that is the invariance under diffeomorphism. So how is the invariant under diffeomorphism taken into account in my theory? Well, it's done by the fact that it's possible to introduce graph states. And I wanted to stress the fact that the graph states here, they are just using auxiliary tools. They are not how to say, they play in a sense the same role as the manifold in the classical formulation of GR. They are dispensable. They are not necessary for the formulation of the theory, but they are extremely useful. And they allow to encode adjacency relations between my quanta of space-time in a way that is completely diffeovariant. So they give us a way to tell which quanta of space is in interaction with the other, without making any reference to a background space. So this is no different. This is similar to introducing a lattice in the theory, a lattice that nevertheless has different properties than the lattice that are usually used in lattice gauge theories, because it has to be a diffeovariant lattice. I will tell you more in a moment, but let me just mention the fact that so we use if you think of the picture we had before.
So Francesca, you have about 10 more minutes.
Yes.
Okay.
Yes. So what we have is that you can associate to each of these polyhedra one point. So I label with just one point each polyhedra, and I connect the different polyhedra with one link, like puncturing the face of the polyhedra. And what I obtain is this kind of a graph of this kind, where the representations of the group labels the different links, and the nodes are invariant with respect to my gauge group. So remember, this is nothing but the fact that what I was telling before, the fact that each each I should think about each of these nodes as a tetrad sitting there that has this rotational symmetry. So the result is a Hilbert space that is the Hilbert space that has exactly the same structure as the Hilbert space of lattice gauge theories. And there is nevertheless a difference with respect to usual gauge theories, in the sense that, well, let me go to this. In the sense that I told you, I want my lattice to be a gauge invariant lattice. And a consequence of this is the fact that the lattice space, the lattice spacing drops from the action. So there is no reference to the lattice spacing in the dynamics of the theory. And this means in particular that while usually in lattice gauge theories, I take the limit for an increasing complexity of the lattice, and I take the limit for the lattice space going to zero, here I cannot take the lattice space going to zero because the lattice space has disappeared from the equations. So, so one important consequence of this is that, well, I have a formulation that speaks very well with lattice gauge theory. So if you ask how is matter coupled in loop quantum gravity, well, you have just to couple matter in the usual way in which you do it in lattice gauge theory. So you can put your fermions on the nodes. So you can populate your lattice with the fields. So instead of having your, if you want, you can start with a lattice theory that instead of sitting on a background geometry sits on another lattice. And the magic here is that because in the theory there is this dropping of the lattice spacing, and this is a direct consequence of the fact that there is also this minimal area and minimal length, etc. Well, when you sit your matter fields on this kind of lattice, you automatically have a regularization. So this takes into account the presence, takes in cure the ultraviolet divergences that appears in quantum field theory or quantum and lattice gauge theories. So if you want to, there is a very nice marriage between the matter fields and this theory of quantum gravity, in the sense that quantum gravity in this way provides a natural cutoff, a natural ultraviolet cutoff that cures ultraviolet divergences. So just to conclude, one last thing that I think is very important. I just wanted to give you the dynamics of the theory. So you see, this is my theory in one slide. I told you that there is this Hilbert space. We said that the Hilbert space is given by a Hilbert space that is similar to the one of lattice gauge theory. We spoke about the observables of the theory that are all constructed starting from the tetrads. And now we needed to discuss how the transition amplitudes are defined. And the transition amplitudes have a straightforward way to be understood once you write the theory properly at the classical level. So let me.
We were disconnected.
Oh.
What was the last thing we heard?
That slide.
So it was on that slide, but.
Okay, I remember there was a moment in which the recording said stopped.
Yes, that was the moment. Yes.
So what I was saying is the fact that I can write the action of general relativity in this form. So this object is just the action of general relativity. If I plug this here, this is just general relativity. But writing in this way the action gives me a relation between different components of this B field. And so this relation is general, but there is a way to understand it that is more transparent once I put myself in the time gauge. The time gauge is the one in which when I consider my region of space-time, I take my normal to be to the region, to the boundary, to be exactly a time-like normal. So in this way, so this allows me to tell you what this relation is saying, that is just a proportionality between these two parts of the B fields, these components of the B field. So this part can be interpreted in the time gauge as the boost, and this one we saw before, they are generators, they are basically rotations. So what I have is that the whole dynamics of general relativity can be understood in terms of this relation, that is a proportionality between the boost and the rotations via this constant that is gamma. So this is completely classical, but now, of course, the quantization amounts just to promote these two objects to operators. So we saw before, we had already done this part in which we promoted L to operators, and we saw all the different geometrical quantities that can be constructed. But now I have this relation between L, the rotations, and the boost. And here I have some magic that happens because, so look at this definition of the L. The L corresponds to, oh, here there is, sorry, there is a typo. There should be, so here there is E naught wedge EI, and here there should be EI wedge EJ, okay? So this is in a straightforward way an area, but here I have something else that I would call a Lorentzian area. So what is a Lorentzian area? Well, a Lorentzian area is the one that is spanned by an accelerated observer in the Minkowski plane. So if I take like the area, so from this Rindler wedge, I take the area that is spanned by the motion of, actually, sorry, not the motion in time of this accelerated observer. So you can think of an observer that is, for instance, one way to see this is to think about an observer in a gravitational field that, in order to keep the position with respect to the gravitational field, keeps on accelerating. So for instance, if you have an observer that is sitting next to a black hole, so of course the natural motion would be to fall into the black hole. But if you want this observer to keep their position with respect to the black hole, so this observer will be accelerating, and in time it will span this Lorentzian area. So what the simplicity constraint, so this relation between boost and rotation is telling me, is that there is actually, first of all, a relation between the energy. So I can associate a boost Hamiltonian to this generator of boosts, and there is so therefore there is a relation between the energy, and we say this is associated to an area. So there is a proportionality between energy and area that, in fact, I mean, if you just consider the Uru temperature of this accelerated observer, so you divide your energy by this temperature, and what you find is that there is a proportionality between the entropy and the area, with the right 1/4 factor. So notice that there is therefore nothing mysterious about the fact that when we look at the thermodynamics of black holes, we find this relation. So and most importantly, the proportionality between energy and area, or the proportionality between area and entropy, is something that one can derive directly from the action of general relativity, written with the term that includes the term proportional to my gamma. So this is an important way to understand that there are no hidden degrees of freedom. We can talk about the thermodynamics and of the gravitational field and having this relation. So this relation is somehow very often celebrated as a possible indication that there are some underlying degrees of freedom in general relativity, and therefore there should be some emergence of space-time from a thermodynamical limit or from a fluidodynamical limit. And here what I'm showing you is that no, I mean, this relation comes from just considering the dynamics of general relativity itself, and in some formulations like, I don't know, Verlinde gravity, or also in the celebrated Jacobson derivation. So what in fact is happening is that they are using the simplicity constraint there. They are using this relation between boost and rotation that is in the dynamics of general relativity. And the last thing that I wanted to show you is that there is much more, because the simplicity constraint in itself show you also that in a theory in which based on this simplicity constraint, you don't have any curvature singularity. Why? Because now, because of the relation between boost and rotation. So remember now, we said that this term, the rotation, once it is quantized, gives a discrete spectrum, but this induces also a discrete spectrum here for the boost. And more precisely, what induces is the presence of a maximal acceleration. So what is happening here is that this accelerated observer cannot accelerate in an arbitrary way, because there is a minimal Lorentzian area. So there is a minimal, a maximal possible acceleration. And it's very well known from all the results in which people were just postulating the presence of a maximal acceleration, that once you have a maximal acceleration, this implies the absence of curvature singularities. So I wanted you to notice something at this point. This is the fact that singularity resolution in quantum gravity, it's something that has to do, on one hand, of course, with the fundamental discreteness of geometrical quantities at the kinematical level, but it's also related to the dynamics. So the full understanding of singularity resolution, singularities, I stress again, curvature singularities. Of course, the notion of singularities is much wider, and one should discuss all the different possibilities. But as long as we are interested in curvature singularities, that are the physical one, that are the one that potentially would disrupt the structure of space-time, well, these are absent in loop quantum gravity. They are absent, well, not just in loop quantum gravity, but they are absent in any theory that is based on this dynamics, on the dynamics of GR, and in which you consider the quantization of the simplicity constraint. So at this point, so this yields this connects with cosmology, of course. So what I wanted to communicate is the fact that in cosmology, there is a long history in the sector, the cosmological sector of loop quantum gravity, that is called loop quantum cosmology, discussing the fact that there is a singularity resolution there. And in that case, people analyze case by case, space-time by space-time, in which way the singularity avoidance is achieved. But what I'm telling you is that, in my opinion, the way to go is to look at the full theory and extract from the full theory the informations that are relevant for cosmology, for black holes, and so on. And then we can work with models in which we import this fundamental piece of truth, some piece of information that is going to stay valid in whatever approximation we are going to take in the different physical models that we wanted to consider. I know I don't have time, and I wanted to give space to questions. I just wanted to add one more thing, because so the remaining, my hope was to be able also to talk about cosmology. I have to skip completely this part. I know you had also some nice reading group regarding this, but what I wanted to tell is the fact that this way of think of quantum gravity can be used in cosmology, and in particular, the current research that I'm doing with my students concern the study of an Hartog-Looking state for cosmology. And in this context, so what we are able to do is to describe a state, so that you can see as a state from nothing into some three-dimensional geometry. But in fact, what we have is a superposition of three-dimensional states that are compatible with a given four-dimensional Lorentzian space, meaning we have a quantum state with all its fluctuations that is determined by the dynamics itself. And what is nice with respect to other approaches to cosmology, to quantum cosmology, is the fact that this state is fully valid, is fully viable in the deep quantum regime that we associated with the Big Bang. And what we are doing these days is to study the quantum fluctuations of this state and look for correlations in fact, look for entanglement entropy between different regions of this Lorentzian space-time geometry. And so this is a way in which we can predict from the full theory what could be the properties of a cosmological states as it could have been in the primordial universe. So the goal of this research line is to try to predict different properties, in particular the primordial quantum fluctuations that, you know, then are at the origin of all the structures that we see in the universe. And so work from the full theory to make predictions. And again, it's a way to work in which we work with the full theory without taking symmetry, doing approximations, but working, of course, with the full dynamics of the theory, working with tools that are fully viable in the deep quantum regime, and trying to extract informations that we can use to make predictions for cosmology. And of course, similar strategies are followed today also for black holes and for other contexts in order to make predictions. Because in the end, what we want is to connect with experiments, and there is this mantra that we don't have experiments for quantum gravity, and I think it's a wrong mantra, because of course we do have quantum gravity measurements. In particular, we have quantum gravity measurements from the sky, and we have a lot of information about what a theory of quantum gravity should look like, and it's just a matter of taking into account all the things we have learned so far, and work with that. So to conclude, so I have tried to give you the flavor of one full proposal for a theory of quantum gravity that is well defined. So they have transition amplitudes that are finite, that has a positive cosmological constant that is four-dimensional Lorentzian, and has a classical limit GR. I dare say that there are not a lot of options today on the table for theories that are able to do this. At least there is one theory with which we can work, and we can try to develop to make both at the conceptual level to understand more covariant quantum theories, and possibly to make contact with observation. And of course, if you have more questions about this, there is this wonderful book that I recommend. And of course, you are also welcome to contact me. I mean, now we have time for questions, but you're also welcome anytime to contact me for more questions. Thank you. I see people clapping. Thank you so much. I cannot hear you.
Thank you. So I'm going to, so we have, okay, I think we can probably, we started a little late, we've had some issues, so we'll do 15, 20 minutes for questions. Yeah. So
do you hear this, Francesca?
Yes.
Okay.
Just people, please speak loud or come closer. So far I can hear.
Okay, some questions. You may not see everybody who asks questions because some people are out of camera, but so this is a finger. This is already a. All right. So Rasmus, please.
Thank you, Francesca. So, okay.
Oh, sorry, I need
questions. I'll start on this.
Thank you.
Is that...
So I'm I'm a little curious, maybe I just didn't get it, but it seemed as though sort of your t-shirt picture where we get space-time in the end, the story you were telling seemed to stop a bit short because we ended up where we have the polyhedra, and if they are not shape matched and aligned, I guess there will be some kind of twisted geometry. So even just Regge geometry, we need some kind of additional story, and then we need another story in order to explain how we get a Riemannian geometry from the Regge geometry. So I was just curious if there is any evidence how we might get those final steps done.
Mm. Okay, hello Rasmus, thank you for your question. Okay, I wanted to say the following thing. I think that if you want reality is that there is a quantum theory out there, a quantum theory of the gravitational field, and what we see, what we describe as continuous, is an approximation of that theory, right? So then, am I worried about the mathematical steps that we need to take in order to retrieve the classical limit? Sorry, not the classical limit, but the continuous limit. Well, I think it's an interesting mathematical problem, but I don't think it's the main physical problem. As you rightly said, what we have right now is the following thing. We have, so first of all, let me say that in the construction that I have presented, it's clear that what we have, what we start with are ingredients that are the core of general relativity. So in a sense, it's not surprising that in the end we get general relativity back. The core of the story was this simplicity constraint that codes the dynamics of the theory. And we have a quantum, we have this quantum transition amplitudes, and we have theorems from 2009 that tells that if you take the classical limit of the theory, so where the classical limit, okay, roughly speaking, the classical limit is this h bar that goes to 0. It's a bit more complicated than this, but for the sake of this discussion, you take h bar to 0, and what you have is discretized general relativity, as you said. Why do we have a discretized GR? Well, because we are using this spin network states. So, as I said before, I see that the spin network states as being an extremely useful tool, but they are not the full story in a sense. So what is happening with the spin network states is equivalent to what happens when you have an electromagnetic field in a box. So you have two kinds of discreteness there. You have a discreteness that is given by the genuine quantum jumps, the eigenvalues of my electric field. And on the other hand, you have also a fake discreteness that is given by the fact that you are putting the field in a box. And this kind of discreteness is something that you remove if you take the box away. So with the spin network, there is something similar, in my opinion, that happens. So on one hand, there is a genuine quantum discreteness that is the one I spoke about most of the time. And there is, if you want, a fake discreteness comes from the tools that I have used, in particular, the lattice that helps me to regularize the theory. And this tool, this regularization can be taken away. How? Well, you get the classical limit, you get discretized the GR, that could be a twisted geometry, or if you want, it goes to a Regge geometry, so it's just general relativity in pieces. And then, of course, it's a mathematical procedure to take the limit for my discretization that goes to infinity and recover in the classical limit. But to me, this is just a nice, maybe mathematical problem, but it's not a physical problem somehow. It's just what is the proper way to remove my regulator? Very interesting mathematical problem. I don't see any problem with respect to the physics.
Okay, Jana.
Hi, Francesca. Can you hear me?
Yes.
Thank you for the talk. So I want to understand better the role of discreteness. Right at the beginning, you said that the continuous spectra is a fake, in a sense. And so the position operator should rather have discrete eigenvalues, not continuous ones. And of course, it makes sense if that you're saying space is discrete. But then in that case, so the question is, how should I understand trajectories? How should I understand the free particle, for example? And also, how should I understand momentum? If momentum should also have only discrete eigenvalues, and I have discrete positions, and how should I understand their connection?
Well, I don't want to offer a full, precise description of this. Let me just give my heuristic understanding of this. So, for instance, the thing is that, there is the same distance in terms of order of magnitudes between us and a proton. Then there is from the proton to the Planck length. So when I try to imagine something like a proton, or even, I don't know, a particle that is even smaller, like an electron. If I try to imagine an electron moving on a sea of quanta of space-time, I mean, we are again talking about an object that is many order of magnitudes larger. I mean, how many? Like more than 16 order of magnitudes larger than the underlying granularity. So because of that, it makes completely sense to describe the motion of those particles as if they are moving on a discrete, as if they were moving on some continuous background. What I meant is that suppose you can have some object, some perturbation that can probe the granularity. Well, in this case, then yes, I cannot define the position at a scale shorter than the Planck length. So in this sense, then the position of a particle will be localized with respect to one quanta of space, then to another quanta of space, then to another quanta of space, and so on. So, and once I do that, also I have, in the moment in which my position becomes discrete, the conjugate variables became bounded, so there will be a maximum momentum. And this is not surprising because this is exactly what I was saying before, that quantum gravity provides a cutoff in the momentum. It provides a ultraviolet cutoff. So the two things totally stays together. Practically, as I was saying, I mean, once you consider the scales of the objects that we are considering, of course, it makes totally sense to describe position and momentum in this continuous way. But again, to me, it's an approximation of the story, not the full story. Is it convincing enough, or did you have a more specific question?
Not convincing enough, but I'll take it from now.
Hi, thank you. Very like super simple clarificatory question of like I think a second slide or something. You mentioned an algebraic formulation of GR, or at least formulation without a manifold. And the only one I'm aware of is something like Einstein algebras, which are totally isomorphic to the manifold representation. And so it's they're equivalent really. So I was wondering what you had in mind with that. It was different to that.
I heard you a bit in a muffled way, so I'm not sure I'm captured the correct question. If I got it right, you are asking about the fact that about the role of the manifold in classical GR. Is this correct?
Yes. Yeah.
Yeah. So what I was saying is that there is a lot of debate on the, if you want, on the philosophical interpretation of general relativity, of space-time theories, and I mean, if you think about all the debates regarding the whole argument that for some, even if it was solved by Einstein in 1815, we are still discussing it. I think it's all about the confusion about the role that the manifold plays. I remember, so the point that I was trying to make is that the manifold, so we don't have to identify the gravitational field with the manifold itself. The manifold is an auxiliary tool. And a reason to think in this direction is the fact that we have formulations of GR that are purely algebraic, and they don't make use of the manifold. So because of the existence, so of course this is a posteriori justification that we can use, because I mean, if you wanted to discuss all the debates about the whole argument from the beginning from an historical perspective, of course this argument was not present there, but now we know. We have a better understanding of GR. We know that we have different formulations of it, and we know that again we don't have to identify the gravitational field with the manifold itself. I was proposing the fact that a better way to think of it is in terms of more clarity comes when we consider in particular also the tetrads formulation of GR. But I remember discussions from the philosophical perspective on this. Now they don't come to my mind, but if you write me an email, I can be able to give you references also about
maybe the thing that would be helpful at first is could you point me towards what these purely algebraic versions of GR are?
No, well, I'm not an expert of them, so I am not able to make.
Is it based on the sort of work by Gauche with like Einstein algebras and Leibniz algebras? Is that something that you're thinking?
Sorry, can you repeat again?
Like Robert Gauche wrote about Einstein algebras, which were algebraic formulations of GR, because they've been shown to be totally dual to the manifold, to the normal manifold formulation, and so it's like they're different mathematical representations, but you still sort of have the manifold, you just representing it differently. So I'm wondering if you're really taking the manifold out, or if you're just giving a different representation of the manifold, which is made out of the maximal ideals on an algebra.
Well, okay. I would be happy to dig a bit more in the literature and give you more precise references that I don't have at this moment. The point of view is the one, in a sense, that follows also what Chris and Nick have been saying with respect to in the case of quantum gravity. So let's look at what these things are doing for you in representing space-time. So what the manifold does for you is, in fact, to give you adjacency, the precise sense in which you have adjacency relations between different points. And to me, this is something that can be achieved, can be given using different constructions. So it's not compulsory to give this information that is coding the structure of space-time in the manifold. And in a sense, the use of graph in quantum gravity is exactly a realization of this. So what we are doing is exactly coding adjacency relations and distances and so on without the use of the manifold. And the use of the manifold plays a role in the sense that we need the manifold to connect to the classical theory. But it's so in the moment in which we want to connect with the classical theory, of course, we have to embed these graphs into a manifold. But again, this is a trick to connect with the classical theory. Exactly in the same spirit of what Rasmus was asking before. I needed to get back the usual tools of general relativity, and among these tools there is the manifold too. But I don't see it as a fundamental aspect of the theory. I'm not able to, so I understand that you want more precise references to algebraic formulations of GR. But again, I don't have it. I'm ready right now, but I'm very happy to continue by email and possibly share more precise references.
Thank you very much.
Is it still on topic?
Yeah. No, it's on topic.
Okay.
Just briefly back to Dominic's point. I mean, general relativity has a manifold in it. So anything mathematically equivalent to general relativity is going to have some means by which you can recover the manifold up to diffeomorphism. So I think it would be too strong a demand to say something eliminates the manifold, to say it's mathematically impossible to reconstruct.
I was hearing very, very badly, but I hope you were.
Can you hear me well?
Let's try. Yes. Otherwise, maybe can you come closer to the computer? Yeah.
Okay. Many thanks for the talk, Kurt. At the beginning of your presentation, you said that space-time is a process, something like that, right? It was in the title, I think. So could you please explain?
No, sorry. Repeat again. You were.
Sorry. Here now.
Yes.
Okay. Yeah. I mean, at the beginning of your talk, you said that space-time is a process or something like that. It was in the title.
Yes. Perfect. Yes.
Could you please explain a bit further what you mean by process there? Because I mean, intuitively, we think that a process is something that happens in space-time, right?
Yes, very good.
So now, I was wondering if you have a different notion of process or something that doesn't suppose the notion of space-time.
Yeah, I mean, the answer goes in two steps. The first step is that in a general covariant framework, you can describe change and interactions and so on in terms of in a relational way. So without making any reference to a background space or a background time. So if you want to say that a process is happening in a certain location, you would say that actually, what does it mean for a process to happen in a location is actually to have an interaction with something, with some physical thing that that define the location. So, I mean, this is just following also what you have with general relativity, in which you define localization in terms of coincidences. And coincidence, what is, if not just another interaction, an interaction between two observers. Even artificial observers. And more in general, being localized mean interacting, having one system in interaction with another one. This other system in particular could be the gravitational field. So what we usually mean by a process taking place in a given time or in a given space means that there is an interaction with the gravitational field, possibly. And also the interaction at a given time corresponds to the fact that you are including in your description the presence of another system that plays the role of a clock. So in this sense, you can talk about processes and interactions and so on in terms of happening with respect to clocks, with respect to reference frames that are physical systems that are part of your description of the interaction of the process and so on. So this is one part of the answer. The other part of the answer is okay, given that we can talk about processes without reference to a background, what does it mean that space-time itself is a process? Well, maybe I can share my screen, but this is not really, yeah, well, this is the slide in which I was talking about this. Even though it's not really, so the point is that we are describing so imagine you have only space-time and you take a region of your four-dimensional space-time, okay? So this is this shaded figure here. So how do you do that? Well, as you were saying before, we need something that defines space and something that defines time. So here on the boundary of this region, so in order to define the initial data of my, that corresponds to a geometry of my boundary, what I do is simply to couple here some clock and something that is like a rod. So in this case, what I'm doing is that suppose here at the beginning, I measure a time with a clock and I measure a time and I measure a length with a rod. So this defines my initial condition for my initial state. And then I compute a transition amplitude, and the transition amplitude gives me at a later time another reading of the clock and of the length, let's say, of my geometrical observable. So, and what is here in the between? What is so? What is happening here is that you have a state on the boundary of the region, and what is in the bulk, it's my four-dimensional space-time that connects one part of the boundary with the other one. It connects my state in with my state out. So concretely, in my spin network, so when I do loop quantum gravity, there was this animation here before. So I have one state, let's say a spin network state, and I start with the quanta of space-time. I have some process, so there is an interaction vertex, and this interaction vertex creates some new quanta of space. So what is inside this region is my four-dimensional space-time, but this is also where I have my interaction vertex. This is a process that takes me from a given geometry to another one in a certain, so you can think in terms of a time evolution, even though the full picture is completely covariant. So there is, I mean, of course, you can take a time gauge and you can define a time evolution, but the full, I mean, if you look at the structure of these amplitudes, they don't select a particular time. So what you just have, it's from one geometry, you go to another geometry, and okay, it's there is also something beautiful here from the point of view of the mathematics. What you have is that you have your rotations that are what label the states on the boundary. So you have a representation of SU2 on the boundary. And in the bulk, we said that we have a four-dimensional Lorentzian spacetime. So in the bulk inside here, you have representations of the Lorentz group. And remember, so if you, so let me tell you just a very interesting thing of the irreducible representations, unitary irreducible representations of the Lorentz group. What they are just 2j+1 copies of rotations. So it's like a diagonal block matrix with a lot of rotations. So the full dynamics of general relativity is coded in the way in which the rotations that are on the boundary are mapped into the rotations that are on the bulk in the representations of the Lorentz group. So what is here inside, as I said, so you can imagine that in this bulk inside here, you have your four-dimensional space-time, you have your Lorentzian space-time. That is where you have the vertex of your theories, where you have the processes. And again, these processes are not happening in space-time, they are space-time itself. So the vertex is creating space-time. And yeah, and I hope I gave you a bit of...
Okay, many thanks. Well, okay, I think, so with apologies to people who are still in the queue, I think we probably should call it a... There we go. We should probably say thank you to Francesca again for a great talk.